make some things. And so one of the things we're going to make is this smart motor. So we want to design a motor that's capable of cognition, a smart motor with AI built into it. So what we're trying to do is sort of build AI into things, so that we have intelligent devices like smart motor, smart sensing, smart meta sensing, and self-driving vehicle, that goes anywhere, like, hey Nessie, go get me groceries, and then Nessie drives over to the grocery store, picks up groceries, brings them back. Freecle, the Freecle project, which is also brain controlled, so that it can work for quadriplegics. We made the first brainwave controlled wheelchair a while back, and we won IEEE competition. And my student Chris Amey got to fly down and present it at the big conference. So that was fun. And so we want Nessie to have that functionality so that Nessie can drive you around on brainwaves, or you can at least control some of the functions with brainwaves. So that's kind of one of the things that we're doing. And the smart motors is the other thing, that you can see if you look at the swim motor page, the brainwave controlled motors and smart motors. And this is making the sensing of sensing and meta sensing. So if you go to, I just got some flanges today, I ordered some flanges for the motors. So we're doing everything at small scale. The idea is you learn the fundamentals here. So we built these super small motors, or systems, small control systems. So you're going to use these really tiny little motors to start with to learn how to do these sorts of things, and then we'll gradually grow to larger systems. So if you look at this web page, so that's a brainwave controlled motor there, controlled by the Interaxon Muse, and then what we've got is we've got the swim on the motor so that we can see and use sort of biofeedback and start to understand the electromagnetic fields inside the motor. This is just a 2-pole motor, and so you can see it's only got one lobe. So the number of lobes is equal to half the number of poles. So you can see there's only one lobe here on this motor, whereas this motor has 6 lobes on it. So this, instead of being, whereas this was a 2-pole motor, this would be a 12-pole motor. And so you can see the patterns in the motor and understand how the motor works. So it helps us to connect with and understand and see and visualize and really get to know the motor inner workings so that we can design intelligent motors and build the AI right into the motor hub, which is quite common. You've got a lot of control systems. If you look at some of these newer motors, they do have quite a bit of intelligence built into the motor. And so you want to have some adaptability or adaptive function in the motor to adapt to varying torque, varying load. This is the swim motor here in this classroom, and we've seen that before. So there's some good examples of it here. This is simply, you can see the swim on the motor turning around. So now we made a little lab kit, and then we made a little lab kit with the motor, and I call it the ece516 lab kit. This is a picture that I took yesterday of the ece516 lab kit. So, and this is just cardboard. So I invited a couple of people, Ben and Emily came over to my lab, and we just show them how to cut out cardboard and stuff like that. So just to cut out a strip of cardboard. This is a really good fast prototyping method just on cardboard. So this prototype here, you can see, is just printed on this strip of cardboard, or cut out on this strip of cardboard. We can laser cut this as well too. And so we're going to, at the MyHull Center, I'm going to prepare, I'm going to design a better frame, maybe in 1/8" birch plywood.
You want me to bring the scraps so we can show them?
Yeah, I'll bring up the scraps where we got just got back from the MyHull Center. I'll pass around some samples of what it's like so you can see what the material is like and how it cuts. And sort of thing.
These ones are good.
So it's 18 by, yeah, why don't I just pass around the full sheet so they get a sense. So the laser cutting size is 18 by 24, 18 inches by 24 inches. And that's the standard
Thanks.
size, and it's 1/8 thick plywood. I'll pass around these two pieces here so you can get a sense of what it looks like and what we can cut out. And so what we're going to do in this case is we're going to cut this out of the plywood. We're going to cut a long strip of plywood like this with the right counterbalance and drill the 3 holes to mount the motor. 1 hole for the shaft and 2 other holes for the mounting screws. They're 6 millimeters apart. Be comfortable working with inches and millimeters. One thing that bothers me about modern CAD is you can't have mixed systems. It'll convert always to one or the other. And I want someone to build me a CAD system that I can put, because a lot of times I know the width and height of something. I'll often say I want holes that are 1/8 of an inch in diameter and 6 millimeters apart, for example. 35 millimeter film is sold by the foot. It's 35 millimeters wide, but it comes in 25-foot rolls, 50-foot rolls, 100-foot rolls, and 200-foot rolls, 400-foot rolls. And so people talk about footage. I got some great footage last night. Well, that means how many feet of film you recorded. Usually that's called footage. And so that's a common example of something. The width is metric and the length is imperial. So we often work in a mixed metric imperial. This is exactly 24 inches, which is 2 feet, by 18 inches, which is 1.5 feet, or 1 cubit. A cubit is 18 inches. So it's 1 cubit by 2 feet. So we should be comfortable working in different units of measure, not just metric. Smoots, for example, is a useful unit of measure. Do you guys all know what a smoot is? Never heard of a smoot? Okay, well, Oliver Smoot from MIT, he became the top guy in the world on standards. He became the world's leading expert on standards. Anyway, in his fraternity, they wanted to measure the bridge to MIT, the Longfellow Bridge. And so they laid him down on the bridge and marked it off in one smoot, and they picked him up and moved him along and marked him off in another smoot. And he was 5'7". That was his height. So a smoot is exactly 5'7", which is exactly 67 inches. And so they marked him off. They marked the bridge off in smoots, just as a joke for the fraternity, just taking off with the writing numbers on it. But then over the years, there were various car accidents that occurred on the bridge. In the police reports, they would write in how many smoots. The car skidded a distance of 5. They didn't know what it was, but they just assumed that those numbers meant something and started using them. And so they were used in quite a few police reports and various other reports. And so when they redid the bridge, repaved the bridge, the police department actually contacted the fraternity that did the original prank and asked them, would you guys please put the numbers back on the bridge, because it's consistent with all the previous police reports, because they kind of found out where the numbers were, and eventually in court cases and everything it determined what it was. So they put the smoots back in. The city also cooperated by putting the little dividers between every, the little expansion joints that are normally 6 feet apart. They made them exactly 67 inches apart, exactly 1 smoot apart. So they established that as a unit of measure, and it's a very well-known unit of measure now. The MIT radio station broadcasts at a wavelength of exactly 2 smoots. And so we call that MDL, it's minimum description length. Don't convert it to millimeters, just use smoots, because it's just 2 smoots. It's really easy to write, it's easy to think. Same as this, it's 2 feet. You don't have to convert it to metric. Don't tell me how many centimeters it is, or how many millimeters it is, or how many angstroms it is. Just say 2 feet, because it's easy, right? And put it down. It's about 1 foot, 2 foot, bang on, right? And it's easy to understand. Everybody ought to know what a foot is. Everyone ought to know what a cubit is. A cubit is measured like this along the hand, and that's 18 inches. And that's a unit of measure that's been around for a long time. A hand is 4 inches, a hand span is 4 inches, finger width is 3 inches. Hand span like this is 9 inches. Those are common units of measure that have been standardized, but they're approximately match the human body, and they're easy for people to understand and associate with. So that's good. And then we might be having metric distances, like we'll have 6 millimeter hole spacing on here. Thing's going to be about 1 inch wide, perhaps, and it'll probably have 6 millimeter hole spacing. So I'll pass this around. You can see how the laser cutter works. When we draw on there, we use the color red to represent a cut. So fortunately, I'm so happy to see that the Myhill Center is using Inkscape. because it's free open source. They're on the right side of the ethics. Remember, immersivity is also a code of ethics at the nexus of the physical, virtual, and social world. The ethos of immersivity says do no harm to the environment. It's free open source. Ethos of technological unconcealedness, which is called aletheia in Greek, which means truth. The Greek word for truth is aletheia, which means unconcealedness. Aletheia is concealedness in Greek, and in front of something is a negation. So aletheia means unconcealedness. And so that's what truth, the concept of truth in Greek, and that's kind of what we need is this code of ethics. And also the right and responsibility and ability to change and modify technology to suit individual accessibility requirements and so on. So those are our principles. And the third branch of society is do no harm to others, including other species. So that's kind of where we're at with Inkscape, and it's really easy to use. And you just use red to represent a cut through, and you use blue to represent etching, and you use grayscale to represent raster. There's three kinds of operations on a laser cutter, and they're referred to as, at least within the MyHull Center, the language is raster, etching, and cutting through all the way through the material. So I'll pass this around as well. Let me pass this around on the other side so everybody can get a chance to see it up close, so you can see what it's like to be able to cut something out. You can cut quite intricately in a variety of materials. It's really easy to do, and this is acrylic. You can also cut, say, black acrylic like this. I'll pass this around as well, so you get an idea of what materials are available. See, the problem with the acrylic is it's not that stiff, though. It flexes under load. See, it bends quite a bit. So I think
That's rolled, that's why.
the plywood will be stiffer.
Yeah.
So this is the swim motor. And so you see it's roughly balanced at the point of the motor. So the motor shaft, we've kind of designed it to balance. By the way, if anyone wants to help with the design, I'm designing this now. Is anybody here good with CAD? Yeah? Got 2 people, 3 people. So Ben and, is it Adrian? And who else do we got back? Newer. Newer. So Ben, Adrian, and Newer. And Meta, of course. You want to take a note,
Sure.
Meta, of the, and we'll get to, grab me after class and I'll show you what I'm trying to do and we can work together on this.
I already have Adrian. I know Noor as well. I'll have them.
Okay, cool. So we'll get together and we'll design this thing. And I'm designing a lab kit, which we're going to use in this course specifically, and I'm hoping to get the rest of University of Toronto to use it, and we're hoping also to get my alma mater, MIT, to use it, and also to get Stanford to use it. So I'm also connected with MIT, Stanford, and University of Toronto, and so we want to get all 3 universities using this kit as a teaching tool. So we're going to design it and distribute it. The next rev, I'm going to build a circuit board, and it's all going to be on a circuit board. But for now, we're just going to take a piece of birch, 1/8 inch, cut it out to shape, mount everything on it. And what's on this kit is a motor, a row of LEDs, and a breadboard, and upon which you place a microprocessor, and then there's a battery. And the idea is to get the battery to counterbalance, so we want this whole thing to be balanced. So you can see here, it's roughly counterbalanced, so that it spins around and makes a 2-dimensional display in polar coordinates. And so that allows you to then display phenomenology as well as other things. I've got a grat on here, a graticule, those circles. These concentric circles are not part of the motor current. That's graphic. So there's sort of 3 kinds of content the swim can display. It can display text, graphics, and graphs, of course. And it can also display image content. So there is this multiplicity of formats that it'll display. So if I turn that on, of course, it will light up the graph. There's a graph here. And if I turn the shaft of the motor, you'll see the motor, it's a DC motor, so when I turn the shaft clockwise, it predominantly comes down here. And when I turn it counterclockwise or clockwise, depending on which way you're looking at it, if you're behind me, it's clockwise now. Facing the motor, it's counterclockwise. So facing the motor, if I turn it counterclockwise, it produces a positive voltage. And if I turn it clockwise, it produces a negative voltage. See, now I'm turning it clockwise. You can see it's centered here, it's pulling it down. You see here, it's pulling it down. When I turn it clockwise, make it like this, it's reducing the voltage. It sits in the center roughly, and when I turn it counterclockwise like this, the voltage increases. And in fact, so if I attach this motor in a vise or other firm fastening mechanism, the motor will turn the vise, but the vise is bolted to the workbench, so the motor will turn the workbench, and the workbench is firmly attached to the ground, so the motor turns the ground and the building and the earth and the universe. And you're part of the universe, so the motor turns you around, and therefore you can see the rotating magnetic field in the motor in the coordinates in which you're exactly standing still, just as if you were an ant standing on the shaft turning with the motor. So I'll pass this swim around so that everybody can take a look at it, and then Ben and Adrian and Nur and Meta and myself will get together, and we're going to design this and send it and make one available to everybody. So I will probably end up subsidizing the class and providing from my own funding something for everybody. I'm going to make a little kit that you can buy at a very modest cost. The kit's pretty well ready. We've got kits ready around, it's around $50 or $60 for 2 people, not too much. That's, $25 to $30 each person. So it's a lot cheaper than most textbooks, and provides a kit that allow you to be at the forefront of AI and machine learning on motors and mind over motor and those kinds of things. So I'll pass this around so everybody can take a close look at it. Try to think about how we can balance the weight. What should we use for a battery? This USB battery roughly balances the weight. If I hold the shaft of that motor, I can't grab that strongly enough to get it to turn me around, because but anyway, you can see that. And then we're going to make something to grab the shaft. So this is something like this. I drilled a little hole in there, and maybe that will help. So there's a tiny little hole in the end of that piece of wood. It takes that and then very precariously almost does it. Anyway, I'll pass this around. This is a first prototype just thrown together in a hurry, but of course we're going to spend a little bit of time and do it right. There's a microprocessor on there, ece5162024jan17. So you'll learn about microprocessors, you'll learn about how to program, how to implement AI and machine learning in a small microprocessor. So we're going to teach you in this course all of these things like Internet of Things, digital twins, extended being, extended body, extended intelligence, extended reality, all these sorts of things that come up in the CTSOC, Consumer Technology Society, where we presented, where I gave the keynote in Las Vegas on this extended verses XV. So hopefully this will give you the background you need to join into this world. So we're right in the middle of creating Lab 2 now. I'm going to make it a little bit different than last year. So I think I want to emphasize this machine learning, motors, smart motors, things like that. And then we'll use that as a calibrator for doing the photocell experiment as well. But I also want this thing to present in its own right as a useful tool for understanding the world, because it allows us to understand Internet of Things. With the ESP32, it's a full IoT-enabled microcontroller, so you can build smart things. So at MIT, we called it Things That Think. That was the term we used. And some other people call it Internet of Things. Lots of people come up with different names for the same field of research. That often happens. But anyway, I want to bring you the world that we created at MIT in the early 1990s and how to make these smart devices. So you can see as you turn that shaft how it rides up and down, And so it gives you some idea of how this motor can be used. We can learn something about motors here. We can learn a lot about how the inner workings of the motor function. And so I want everybody to have that background. And then let me see if I can find. If you search Manu on XV, you'll probably find this paper. And let's see if it'll let me actually view it. Because I'm here on campus, I should be able to view it. I shouldn't need. There it is. So that's so this is the whole idea of XV, extended versus, and all this kind of other forms of sensing. And then we've got the ESP32. I'll give a better explanation or introduction to all of this. Let me just grab that. So by the way, this thing here is uft.me/myfab. That's where the MyHall stuff comes up. This is a little journey around the MyHall Center. That's the swim, how it lines up with this board. We're going to have to figure out how to get it. I want us to figure out how we can cut this out of a 2 foot by 1.5 foot piece of birch. So it's a little long. So what I'll probably end up doing is having a hub. We might do it in 2 pieces. We might have a hub part with a spoke part that comes out of it or something of that sort. Yep.
We could put a box on top of it, put the batteries, so it could suspend above the motor, so we don't actually have to have the extra length. So it would just stay on top, and the center of gravity will stay the same.
Above the motor, or? Above
the motor, cables from the rear, and use A2 batteries, like 2A batteries.
Yeah, we could use 2A batteries, or we could use an 18650.
Yeah.
We got to figure out what we're going to use for batteries to counterbalance, and I'm open to ideas. We'll discuss this after. Like if anybody wants to help with the design, we're going to come up with something pretty quick because I want to get it out. We want to get it out to everybody in the class, give everyone in the class an opportunity to have this. But anyway, that's how it looks in relation. That's how it looks in relation to the device. This is some shots of the rough prototype. And then this is the pinout of the ESP32 processor. So the upper left 4 analog inputs are the only ones that really work reliably. GIO, P, 36, 39, 34, and 35. Those are the only 4 that work reliably. So the 4 that we'll use on the upper left, we'll put that on a breadboard. And because this is an overall design that's used for lots of other things, a lot of those other pins have multiple uses that conflict. If you want to use any of the IoT capabilities like Bluetooth, Wi-Fi, all this wireless, it clashes with some of the other analog inputs. So there's really 4 analog inputs that don't conflict with anything else. So try to think in terms of 4 analog inputs. Usually I use 3 of them for the 3 phases of the motor, and then 1 of them can be for the photocell, so that you can use them all at the same time. And you can have you'll be able to have other sensors. You can connect an IMU, for example, inertial measurement unit, 9-axis IMU, including compass, or some people think of a 10th axis as a barometer pressure sensor, is another will be another useful input to make this thing respond to the world around it. So what you'll learn in this course is how to build intelligent devices that use AI and machine learning humanistically to connect to the physical world and to connect to the social world. So I like to call it social physical AI, physical AI, social AI. It's connected. Immersivity is what we sometimes call it. Is the idea is that the AI, the learning, the machine learning is connected to the physical world by way of all these sensors and actuators. It's connected to the social world by being connected to others as well. So that's what we want to learn here. So the sequential wave imprinting machine is one thing we often talk about is the metaverse. And this is Meta, is a company that I founded together with my student Raymond Lowe, as well as Ben Sand and Myron Gribbets, two others. 4 of us founded this company, and that's our original logo. The logo was inspired. For the logo for Meta, I wanted something that was a light, something in light, to draw with light. So I was playing around with the idea of drawing shapes and patterns with light and with high voltage. Sometimes I use sparks that don't quite meet the gap and bring it up to some material and draw. Or I'll use LEDs or incandescent bulbs. So we wanted this idea of writing freehand, of using the human hand as the input device, which is what metabacography is. So this is kind of work I did back in the 1960s and 70s on defining metasensing. That's our Meta computer, and connected to the Meta 2 eyeglass. That's my office at the headquarters in Silicon Valley, and got the violin on my desk there with a sequential wave imprinting machine. And so this was a kind of exploration into sensing and metasensing. We're just having a little bit of fun with our company logo there, lighting it up with the SWIM sequential wave printing machine and that sort of things. So you'll be able to have some fun with this kind of stuff, metaverse. What I used to call it back in the 70s is metavision, the vision of vision, sensing sensors and sensing their capacity to sense, sort of predecessor of metaverse. So if you look at metavision, wearcam.org/meta, there's a little bit here. You can read that paper in extended reality to get a sense of the background for it. And then metavision, this is metavision, the sensing of sensors. And I demonstrated this to one of the students yesterday, the camera. Metavision is the vision of vision. It's the sensing of sensors and the sensing of their capacity to sense. And so it's a predecessor of the metaverse in the sense that in the 70s, I was interested in things, social technologies that use these sorts of technologies. This is a SWIM here, for example. Grab this and just see this is a SWIM, and it picks up different phenomena. And you can wave it. We can put light sensors in here, or it can be sensitive to light. And as you wave it back and forth, it can respond to things and respond to things about things. So it can respond to sound waves, for example. You can wave it back and forth and see sound waves. I want to bring more and more, I'm feeling this course wants to bring you to the roots of things, to the origins of things, because there's so many courses on AI now that teach it at the surface level. I want the foundational knowledge of these things and how they originated and how a lot of these ideas came about originally. So I kind of want to give a grounding for some of these things in this course. So when you'll have a kit like this, you'll be able to wave it back and forth and see sound waves, for example. That's easy to understand, how you have a microphone on here and it just sees the sound waves and shows you the sound waves. That's simple, of course, like if I go to, but then I think the metavision is taking it a step further. But let me see if I just go to, if you go to wearcam.org/swim, sequential wave imprinting machine, and scroll down to the bottom, and click on New Swim. There's some examples here of seeing sound waves. How do you see sound waves, and how do you understand sound waves? So this is something really easy to understand to begin with, because the concept of metavision is a little harder to get. But this is Pete playing a trumpet. Trumpete, I call him, because he always walks around with a trumpet. And so you can see the sound waves coming from the trumpet there, with the swim waving back and forth. So that's pretty simple, right? You've got sound waves from a trumpet. But what's a little harder for people to get their head around is seeing the potential for sound waves to be created. So what that is seeing sound, seeing a sensing device. Like this is a bug sweeper here. There's a microphone hidden inside the nose of that stuffy, and what we have here is a wrist-worn swim, which allows us to see the potential to listen. So what we're seeing here is not sound waves, but it's the capacity of a microphone to sense sound waves. And so that's a kind of bug sweeper, which gives a complex valued output whose magnitude is the strength of the bugginess, let's say. How well that mic can listen is represented by the magnitude. This is the real part of the metavalence wave function, whose magnitude is the strength of the ability of that microphone to listen. So if we plot the real and imaginary parts of the metavalence wave function, we get a complex valued wave that's decaying as we move further away from the microphone. So we'll start to understand some of those concepts. This is metavision in the sense that it's a shared reality that doesn't require any eyeglasses. So you'll be able to show it to your friends and they can see and understand it. I'll just give you an example. I'm just going to grab a swim here so you can see it, because yesterday I had one of the students was saying, hey, what was that? And I said, oh, this is a swim. It's a sequential wave printing machine. Meta sensor to sense the sensing of sensing sensors and to sense their capacity to sense. I'll just turn off the lights here a little bit. Hopefully there's enough light from that TV that you guys can still see a little bit. And what I should do is I'll block out also the might have to get it dark here a bit.
Should I close the door?
Let me see. You guys might be able to see it. I think it's dark enough in here. You'll probably be able to see it. Let's see. If necessary, I'll get the. If any of you have trouble seeing this, let me know, and I'll just black out the
Go back.
window. So who wants to be a volunteer? This is a toy gun. My daughter had this toy gun, and I mounted a camera onto it. And when you squeeze the trigger, it takes a picture, and when you hold the trigger down, it takes a video. And it's kind of like a fun little video game in the metaverse. Well, before the term metaverse came up, back in the 70s, I called it metavision. But I guess nowadays you'd call it the physical metaverse is what I would call it, because it's the metaverse connected to physical reality. Anybody want to volunteer as the photographer?
She raised her hand up.
Huh? Okay, so grab this gun here, and what you want to do is, we're going out on a shoot here. Yeah. So squeeze the trigger. Now see, notice when you squeeze the trigger, these lights come on. Now squeeze it again. Hold the trigger down, actually, and it'll shoot video when you hold the trigger down. So you can see these lights here glow when they're being in view of the camera. When the camera can see them, they glow. And when the camera can't see them, they don't glow. That's a surveillance camera, by the way, in case that's not obvious. Pelco surveillance camera that you might find at a. Now squeeze it and hold it down. Now, you see when I move this, can everybody see these lights? And if I move this back and forth, actually, if you just hold the camera still, you can see when I move this back and forth.
If you do it this way, like go to the side from here so that they can see.
Yeah, I'll stand over here as well so that everybody on that side can see. So you can kind of see when I move this back and forth, the lights that are in the view of the camera are glowing. Now what I'll do is I'll quickly, if you hold it still there, just keep it still, I'll quickly move this up and down like that. Now can everybody see, if you don't let your eyes follow the swim, the trick with a swim is to ignore it. Swims are made to be ignored. If you let your eyes follow the swim, you won't see the phenomenon. You have to pretend the swim's not there and look at this. Just look at the gun, or keep your eyes fixed at one spot and don't let your eyes follow the swim. Can everybody see that sort of rectangular shape in front of that? Can everybody see the raster or the shape? There's a box hanging in space here. Can everybody see that? Now if I come a little further away, the box is a little bigger because the camera now sees more. Can everybody see that? Now, actually, if you turn it this way, maybe I can get it to the point where the rest of the class can see it. Can you guys all see that box here? So when I'm close to the camera, the box is smaller, and as I come further away, the box gets a little bigger. Can everybody see that? Now, you can imagine if this was on your motor and spinning fast, you could actually see it. You have to struggle a little, let your eyes adjust to the dark and stare at some spot to see it, because it's moving slow enough that I have to wave it back and forth reciprocally. This is reciprocating motion, so necessarily it has to be slow. But if I turn this to rotary motion, and I could go around like this, and I could spin it around, then I'd be able to whip it around and be able to see it just like a TV screen with this phenomenology on it. Notice that you don't need eyeglasses to see this. This is the social metaverse, or the physical metaverse. You don't require any special eyeglasses. I built this back in the 70s, the original prototype, not this one, this is a newer one, but I built the original one back in the 70s, and people were really amazed at that. They could see this shared reality that we live in without the need for any special eyewear or anything. It's just physical reality. And then, there you have it. So did everybody see that? You guys can see it from over there too. So if you search wearcamp.org/swim, you can find out more about this. So in any case, let's have a big round of applause for our photographer. And I'll put this back. Good. Okay. Good, so that's an example of the sequential wave and printing machine and the ability to sense and meta-sense. Meta-sensing is the sensing of sensors and sensing the capacity to sense. And I've got, in the next 6 minutes, I'm going to wrap up here with this idea, and we'll get ready for the office hour. And then those of you who want to do Nuit Blanche, let me know tomorrow. Come here at noon and want to get started on that. But anyway, these are examples of meta-sensing. I have a stack of physics books there. I thought it was kind of appropriate to put this little stuffy, cute little stuffy that happens to be a spying, listening microphone. But and anyway, there's a Fourier series, for example. The swims, it gets interesting when you get multi-component with it. Like there's a first two components of a square wave Fourier series. There's a photograph that shows that thing moving back and forth. Again, there's a microphone here, and this is its capacity to listen to square waves. And so that's a fun thing that we will be able to play with, and you'll be able to have lots of fun with. And once you get that thing moving, see if I've got, I was going to look at, oh, here it is. Interference pattern. This is kind of nice because there's a photograph of the capacity of two microphones to listen. And they exhibit an interference pattern, even though there's nothing there. There's no sound. It's not a photograph of sound. It's a photograph of the possibility of sound being sensed. And this possibility of sound being sensed exhibits an interference pattern. So that's kind of interesting. There's nothing actually there being measured. It's just the possibility of something being measured. So it's very meta. And so this is kind of how I spent my childhood in the 60s and 70s, is doing metavision and meta sensing. And so I want to bring this idea because I think it's nice, because it means you don't need special eyeglasses. You can share this, you can build this. It's simple. I built it like when I was 12 years old out of scrap materials I found in dumpsters. So it's not technologically advanced in any way. It doesn't require any massive budget. So you can build it out of cardboard and a USB battery and a radial motor somewhere, so it's easy to make. So because it's easy to make, it's an easy point of entry into understanding metavision. And so I want everybody to start with that foundation upon which we built extended intelligence at MIT. We created this notion of XI, extended intelligence. There's extended intelligence, extended being, extended universe. And so this XV, XI, XR, extended world is something that we'll build and make, and I want to have you join me to build this together. So the lab tomorrow, please get it up to Instructables, your cameras, and then let's get moving on to the next one. And I'll welcome help that any of you have. And if you know anybody else who would like to join this course, please tell them about it. We want to get a few. It'll be good to get a few other people who are really into making into the course, just to round things out a little bit. It'll help all of us, because I can do meta mentorship too. Meta mentorship is mentorship of mentorship. By that, what I do is I mentor others to mentor you, which also helps spread the word a little bit. So get 3 or 4 lead students, like already, Ben, for example, Emily, anybody else who wants to kind of drift into that role. I'll be happy to provide extra mentorship, and then you can help teach some of the other students and sort of be leaders in the class, thought leaders within the class. And so it'd be good to have, if you know anybody else who would like to join and maybe become one of the thought leaders in the class, that'll be really good. And write some papers, get into MIT, Stanford, all those kinds of things. We'll try to push on thought leadership. So let me know, have fun, and then tomorrow, Nuit Blanche at noon here, info session. And if you're doing the info session, I'll cut you some slack on the deadline, so don't worry about tomorrow's imminent deadline. I'm sure a lot of you are hurrying, trying to get that Instructable finished to post by midnight. By the way, Instructables is kind of, give it time. Like when you post it, it might not show up right away, so get it in there, check it, make sure it actually loaded. All right, good. So I think we're right on the nose, 1500 hours. So we're now officially into office hour.